Okay, welcome everybody. Today we have Kristiansen Lara. Actually, we have him again. So thank you, Kristiansen, for being here again. He's a postdoc at Centro de Estudios Científicos, Valdivia, in Chile, and he's going to speak about Hagedorn behavior and logarithmic corrections to geometrized integrable system. So, all yours, Kristiansen.
Thank you very much, Lucas. Well, first of all, I would like to say thanks to the organizers who kindly gave me a spot here in their seminar schedule. Thank you very much. So, as Lucas was saying, the title of this work is Hagedorn Behavior and Logarithmic Corrections to Geometrized Integrable Systems. My name is Kristiansen Lara, and this work is going to be published soon, and it's been done in collaboration with Francisco Reyes, the PhD student from Miguel Pino at Universidad de Santiago de Chile, and Ricardo Troncoso from Centro de Estudios Científicos and Universidad San Sebastián. So, if I will have to summarize my talk in some brief lines, is that first of all, we are going to unveil the equivalence between the asymptotic dynamics of ADS3 general relativity with 1+1 integrable systems. Concretely, through the imposition of suitable asymptotic fall-off and boundary conditions, we are going to unveil the equivalence with Dim's hierarchy. This is the general aim of this talk. In this regard, let me start from scratch in the sense that we know that the unification of space and time as a single entity is encompassed in Einstein's theory known as general relativity. And this framework, this paradigm, this paradigm has evolved in what is known as the holographic principle in the sense of Thorne, Toft, and Susskind. They propose that the dynamical content of a d-dimensional gravitational theory is encoded on its d-1 surface volume. And its first concrete realization was done in a string theory context proposed by Maldacena, known as the ADS-CFT correspondence, the conjecture. Nonetheless, I would like to emphasize, first of all, a precursory result of this duality, which was formulated almost 10 years before Maldacena's article and is the work of J.D. Brown and Henneaux, who showed that with suitable boundary conditions for the gravitational field on ADS3, the theory exhibits asymptotically two independent copies of the 1+1 dimensional Virasoro algebra with the two-dimensional Virasoro algebra with central charge known as the Brown-Henneaux central charge. Well, L is the ADS3 radius and G is the three-dimensional Newton constant. And also, I would like to say that these results do not rely on string theory. So this lower dimensional result emphasizes the role of the asymptotic behavior of fields in order to elucidate holographic properties of gauge theories. So following the lead of Brown and Henneaux, we aim to explore novel asymptotic behavior in ADS3 general relativity to establish new holographic correspondences. But before that, before going to the heart of the matter, let me review some aspects of ADS3 general relativity. First of all, the punchline here is that 3D-GR is a topological theory from the bulk perspective, in the sense that it is a trivial theory from the bulk perspective, namely that the Riemann tensor may be fixed in terms of a Ricci tensor. So basically, every solution of Einstein equations will locally coincide with the value of the cosmological constant. Therefore, there will be no bulk propagating degrees of freedom, such as gravitational waves. Secondly, although that this detail that the theory is topological, well, the theory is interesting enough because it has a black hole solution, the BDZ black hole, which corresponded to an improper identification of ADS3. And also, this theory is nice to explore holographic correspondences. Why? Because it's pure boundary conditions. Boundary conditions capture all of the dynamical content of the theory. So, as Cousaert, Henneaux, and Van Driel taught us, they show that with the Brown-Henneaux boundary conditions, although that the theory has a lack of bulk propagating degrees of freedom, it has boundary propagating ones. And also important, why? Because they allow us to define asymptotic symmetries, and asymptotic symmetries correspond to the set of gauge transformations that preserve the form of boundary conditions. So basically, we have a black hole, asymptotic symmetries, and boundary propagating degrees of freedom. And these features has reached some applications, like, for example, the soft hair proposal from BMS, supertranslation symmetry of Hawking, Pérez, and Strominger, also the celestial holography program, and also my business, which is integrable systems and general relativity. So, what does it mean with this duality between integrable systems and general relativity? Well, before proceeding to address this duality, let me do a brief crash course on integrable systems. Well, we know that many differential equations that appear in nature. Oh, sorry, guys, if you have some questions, please ask. So we know that many differential equations that appear in nature, many of them are nonlinear. Nonetheless, some of them are integrable, and I am going to define what integrability is. Nonetheless, I am going to, before that, give you some heuristic heuristic definitions, and then we are going to be more concrete with that. And I'm going to review a prominent example, which is known as the Korteweg-de Vries equation. So the Korteweg-de Vries equation is given by this nonlinear partial differential equation where the dynamical field is mathcal L, which is a function that depends on T on phi. Here L is the ADS3 radius from the gravitational perspective. This is a spoiler. And also C will correspond to the central charge. So what about the structure of this nonlinear PDE? Well, it has two legs. The first leg is associated to nonlinearity, and the second one is associated to dissipation. Also, this nonlinear PDE can be rewritten in a Hamiltonian fashion. What I mean to that, well, is the following. Notice that the KdV equation can be rewritten as a continuity equation, and this continuity equation allows us to find that this guy can be understood as the functional derivative of some functional H2, where one can read this following quantity H2 like this. While on the other hand, it is possible to rewrite the KdV in this form and observe that this guy L can be rewritten as the functional derivative of H1 with respect to L. Therefore, it is possible to read H1 in this form. So basically, I have rewritten the KdV equation in these two different but equivalent ways, like you can see here, where dv is this operator that you can see here.
Sorry,
So,
Christiansen, a silly question.
yeah, please.
What was so the L dot is the derivative with time, and the L
Yes. Oh,
prime?
sorry, I didn't explain that. Sorry, I forgot it.
Ah,
Yeah. So L dot is the temporal derivative, and L prime is the derivative with respect to phi.
okay, okay, okay. Thank you.
Sorry. So, with the KdV rewritten in this Hamiltonian form, notice that with operators d phi and dv for some arbitrary functions f and g defined on the phase space, it is possible to define the following Poisson brackets. And it is important to show that they are well defined, namely that they are antisymmetric, they fulfill Leibniz identity, and also Leibniz property, and also Jacobi identity. And also that they are compatible, namely that the linear combination of these Poisson brackets yield a third structure, this one that you can see here. So basically, to find these operators here seems a somewhat easy task. Nonetheless, as a second example, I am going to show you a different integrable system, and it is very difficult to find these differential operators that allows you to define well-defined Poisson brackets that fulfills these properties and also that they are compatible. It is a very non-trivial task. I thought that
Christiansen?
here it is trivial. Please.
Hi. I have a question. These operators are uniquely defined? or are there
What do
like
you
a
mean by only defined? Is that in the sense that you can find, for example, a third differential operator such that it fulfills this property?
Yeah, I mean, there you have like dv, but for example, you could have another like dw with
Yeah,
another
I understand.
h0, for example.
I understand. Yeah, it is possible to find one, but first of all, this question has two answers. First, it is possible to find a second one. For example, if you find a third one, then you will be able to say that your system is three-Hamiltonian if it fulfills all of these properties. And the second answer is that, okay, if you are able to find a second differential operator dw, then you must check that this differential operator dw allows you to define a well-defined Poisson bracket. And that's a non very trivial task because you must demonstrate that the Jacobi identity fulfills, and it's very hard to prove it for a different differential operator that you find. So that's the answer that I can give it to you. It solves your question.
Yeah, thank you.
Thanks for the question. So now comes the definition of a B-Hamiltonian system because I didn't define it. Well, a system will be B-Hamiltonian if and only if we can find two compatible, well-defined Poisson brackets. That's it. So heuristically speaking, is that you are able to for the friends is that you will be able to rewrite your favorite nonlinear PDE in two different but equivalent ways, such that they allow you to define well-defined Poisson brackets. That's it. End of the story. So why the v in this differential operator dv? Well, I am going to skip the details, but nonetheless consider the Fourier expansion that you can see here. So basically, according to the definition of the Poisson bracket between L and L, it is given by this expression. So the Poisson bracket between Lm and Ln, it will be given after several steps that I will going to skip. It is possible to find that the Poisson bracket gives you this commutator after the canonical prescription like this. So basically, okay, I'm going to give you the spoiler, but if you recognize CBH like this, basically the Poisson bracket in the KdV equation yield the Virasoro algebra. So now comes a question is that many people in the literature, like they explored different integrable systems with Poisson structures beyond Virasoro. For example, Poisson integrable systems with BMS Poisson structure, for example, but now in the setting of asymptotically flat spacetime. Well, continuing with our task, now we are going to address the definition of integrability in the Liouville sense. So we had this expression that you may read here, and we have this relationship that holds for H2 and H1. Nonetheless, this relationship can be generalized to encompass your favorite nth functional H, and these guys that you can see here are nothing but differential equations in the sense that, okay, you can plug here H1, then you will be able to find H2 here. Then if you replace n by 2, then you will be able to find H3 and so on. And these are the functionals that I am showing you here along here. You can find H0, H1, H2, H3, and so on. It is in fact an infinite tower of functionals. And these functionals, all of them, they will be conserved in time. I am going to show you the proof immediately. And how is the proof? Well, the proof is that, okay, basically you must compute the time derivative of your favorite functional H along the two Poisson structures that you will have. And then I will give you an example through the first Poisson bracket D5. Okay, so now I am going to show you the details because this is important. So with d phi, one can the definition of the Poisson bracket. It is given by this expression that you can see here. So nonetheless, observe that when d phi acts on this guy, notice this relation that you can see here. It transforms to dv, and it lowers one index of the functional h, and this is what happened. And now this is basically the definition of the second Poisson structure V, the Virasoro one. But the Virasoro-Poisson bracket is well defined in the sense that, okay, it fulfills antisymmetry like this. And because it fulfills antisymmetry, okay, one can rewrite the Poisson bracket like this. And then now we apply the recursive relation for the KdV equation that you may read here. Okay, and this recursive relation that you can see here, when dv acts on hn, it raises one index of h. And this is what is going to happen. It raises one index of h that you can see here. And this guy, okay, by antisymmetry, it is this expression that you can see here. And it is nothing like this. So we have this expression that you can see here. And we can apply the procedure m minus n times. And applying the procedure these times, you will arrive to this expression. And this expression, okay, you can contrast it with this guy. And this result, it tells you basically that the time derivative of hn is 0. And you can generalize this procedure for the second Poisson structure V. And that's it. And what does it mean, this result? Well, we have infinite conserved charges, and they all Poisson commute. Basically, in the mathematical literature, they are referred as the involutive conserved charges, unveiling the integrability in the Liouville sense of the system. So, heuristically speaking, think about, for example, in the Kepler problem. In the Kepler problem, one must integrate the equation of motion. One aims to solve the associated integral. Nonetheless, to solve the integral, one must recognize the energy and the angular momenta, and then you will be able to solve the associated integral of motion. Here, we are working in a field theory context. So we will have infinite degrees of freedom. So basically, to solve the associated integral of motion, you will need infinite conserved charges. So that's the heuristic definition of integrability, and in the Liouville sense. And it's, I don't know how to say the word in English, but toma prestado some elements of the definition in finite space, on finite phase space. So regarding the KdV hierarchy, okay, so basically at this moment, okay, we know that integrable systems usually are associated to nonlinear PDEs. Also, they can be rewritten in a Hamiltonian fashion. Also, of course, they are integrable, like the name says, in the Liouville sense. In the Liouville sense, basically that all of their conserved functionals are in evolution with each other. And also, it is possible to construct a hierarchy. Well, by this relation that you can see here, recall the recursive relation, it is possible to construct all of these nonlinear differential equations. Well, this is nonlinear, but all of them, yes. So it is possible to construct all of these nonlinear PDEs, your favorite ones, but all of them, they converge in the sense that, okay, all of them, they have infinite conserved charges, and they have a very profound structure, a structure behind. That's my point. And I would like to emphasize this result that for n equals to 0, we arrive to this differential equation, which is known as the chiral boson equation. The chiral boson equation is the Einstein equation in the Chern-Simons formulation of gravity that emerged when one imposes Brown-Henneaux boundary conditions. That's important. So also integrable systems, they have soliton solutions. Well, solitons, they are very remarkable. What are the definition of a soliton? Well, a soliton is basically a glimpse that travels. It's a solitary wave, but more formally speaking, it is a solitary wave localized within a portion of the space-time. It can be interact with another soliton, and 3, it can be emerged from the collision unchanged. So what I refer to this, well, this is important. Why? Remember that in the KdV equation, we have two legs, one leg associated to nonlinearity and the second leg associated to dissipation. So when nonlinearity uh, interacts in a fine-tuning way with the dissipation, from this interaction, it will emerge a soliton. That's the reason why here it says a fine-tuning. Secondly, solitons, they can emerge by calculations by hand. It is very easy to construct a soliton. And thirdly, recall that in the definition of a soliton, I said that two solitons can emerge from the collision on change up to a phase shift. That's important. Why? Because it's telling to us that basically we have a nonlinear superposition principle holding here. Like you can see in this image, a soliton is traveling alone. It interacts with the soliton emerged from the collision on change. Basically, we have the superposition principle, but in its nonlinear fashion. And finally, with the crash course of integrable systems, we have that these guys they can be postulated as a zero curvature formulation, and this is the linking point with ADS3 general relativity. So consider the two-form curvature that you can see here, where AT and A phi are given by this expression. What are these guys? Well, L0 plus minus 1 are the generators of the SL2R algebra, this expression that you can see here. Then Ft phi will yield you this differential equation, this operator dB acting on mu. Nonetheless, if we recognize mu as the functional derivative of h with respect to L, and you plug the nth KdV Hamiltonian, you cannot plug anything that you want. You must plug, you must do some refined guess in order to arrive to an integrable system. You cannot plug a dog. You must plug something that is sensible to this differential equation. So if you plug the nth KdV Hamiltonian in this expression that you can see here, like H0, H1, H2, and H3, and so on, then the differential equation will transform as the KdV hierarchy. And why it is the linking point with ADS3 general relativity? Well, because basically after some transformations, Ft phi equals to 0 like this is nothing but Einstein equations in the Chern-Simons formulation. Like I will going to say it right now. So because Ft phi is an integrable system and Ft phi is Einstein equations from the Chern-Simons perspective, basically that's the reason why we are saying that we're working with integrable systems general relativity. And why I like this? Well, first of all, it is clear the construction, and secondly, we will work along the Hamiltonian formalism of gravity. And within the Hamiltonian formalism of gravity, you can control what you are doing with the degrees of freedom. That's one of the reasons that I like this duality. That's one of the reasons that I do this.
Kristiansen, so
Please.
this Hamiltonian is related to the chiral boson or something in the boundary?
Yes, I am going to show you.
Okay.
In fact,
and where does
it will correspond to be more precise? It will correspond to an Noetherian charge. Basically the conserved functionals of the integrable systems will be mapped as an Noetherian conserved charge from the gravitational point of view. So basically, I am saying that, okay, integrable systems, I am transforming integrable systems as Noetherian symmetries. That's what I am doing. That's my business, and that's what I will do right now.
Okay.
So other example is the dim equation, which will correspond to the integrable system that we are going to analyze along this talk. KdV equations was a prelude. So dim equation is like this. Remember that I told you that to find the differential operators to an integrable system that fulfills in its Poisson structure, antisymmetry, Leibniz, and Jacobi identity is very hard. So now one will naively try to find the differential operator that allows you to rewrite the dim equation, this equation that you can see here, in a big Hamiltonian fashion. It seems an impossible task. Nonetheless, notice that this expression is nothing like this. This it further simplifies to this differential equation. So, okay, one can readily find the associated differential operators that allows you to write the dim equation in a Hamiltonian fashion, where we have dw and dc, where dw, it will be given by this expression that you can see here, and dc, it will be given by this expression. Obviously, we will have d phi squared associated to this, but dw is novel. And notice the following, is that dv, remember that dv was one of the Hamiltonian operators of the KdV equation, and remarkable, this Hamiltonian operator associated to a different integrable hierarchy, the KdV hierarchy, splits into two different Hamiltonian operators, dw and dc, associated to a completely different hierarchy, dim hierarchy. I'm going to show you dim hierarchy. So, okay, one can find H0, H1, H2 like this. And okay, as I was saying, we have the Hamiltonian rewriting of this nonlinear PD, and the operators satisfy the following recursive relationship. That's the reason why one can find H0, H1, H2, and so on. So basically, under Poisson brackets, one can show that the temporal derivative of Hn is basically zero, or in other words, that all of the conserved charges of the integrable system are in involution. That's it. And also notice that, okay, this unveils, of course, the integrability. And what about a simple solution of the equation? Why it is important to analyze a simple solution? Because with this simple solution, we will construct a black hole from the gravitational point of view. So what is a simple solution of this differential equation? Well, I think that, okay, is the zero mode. So in other words, L is equals to a constant. So regarding dim hierarchy, okay, dim hierarchy for completitude, it will be given by this expression. And notice that also we have the chiral boson here. But now we have dim equation, and therefore the differential equations associated to higher order terms of the hierarchy are very involved. So this is repeated. So regarding the zero curvature formulation, well, remarkable. Well, so I was telling to you that one of the Hamiltonian operators of the KdV hierarchy splits into two Hamiltonian operators of dim hierarchy. So there is a relation between dim and KdV. So remarkable, the zero curvature formulation of dim and KdV, it's the same, in quotes, it's the same in the following sense, that recall that for KdV, we have this two-form curvature that you can see here. So nonetheless, the difference lies in the election of mu, or in other words, in the election of h. Why? Remember that mu was the functional derivative of h with respect to L. So if you plug your favorite Hamiltonian of dim's hierarchy, and you replace it here in the zero curvature formulation with these gauge fields AT and A5, it's the same as the KdV, but they differ only in this form of mu. Then you will be able to find dim's hierarchy. And that's it. So what are the physical consequences of equal zero curvature formulations up to the difference of in mu or h? Well, implies that from the imposition of boundary conditions from the gravitational field, it will imply that they share both KdV and dim. They will share the same falloff from the Chern-Simons perspective. I'm going to show you in detail, but this is the spoiler. They will share the same falloff, but the difference will lie in mu. So choosing different mu, basically different Lagrange multiplier. Remember that Lagrange multipliers are not constrained to the equations of motion. It means different boundary conditions. So as I was telling to you, you have AT and A5, the zero curvature equation. You obtain this differential equation. So for KdV, you have these guys, but now for dim, you will have this guy. How do you obtain dim? By choosing the following mu's associated to dim. If you choose the mu's associated to KdV, then of course you will have the left-hand side, but if you choose the mu of dim, then you will have the right-hand side. I don't know if it's clear. So with this, with this previous discussion, it is possible to define the general objective of this talk, which is to postulate the same fall-off than the KdV boundary conditions, but exceed different boundary conditions. I will abuse of the notation because we have usually people in the literature, they refer to boundary conditions as a whole, while here and in the article that we are going to write with Francisco and Ricardo, we will split fall-off and boundary conditions. They are in a different setting, in a different foot.
Kristiansen?
And in particular, yes, please.
Yeah. So in principle, both systems are different, like the dim and the KdV.
Exactly. Yeah, exactly. They are completely different. Although that they share the same fall-off, the choosing of different boundary condition, basically you are doing like it is very innocent to choose different mu. Okay, you're working with KdV, you're working with the mu's of KdV, and you're happy with that. But now comes your friend, and your friend says to you, okay, but choose different mu. And you will say, okay, nothing will happen. But or maybe you will say, okay, there will be small differences, but choosing different mu that the KdV wants will yield you a complete asymptotic dynamics. I thought that they have the same fall-off. And that's the purpose of this talk. I don't know if it's clear.
Yeah, that's good.
So let me try to emphasize this. I will do it in English, but in Spanish is I think I will do it better, but let me do it in English. So imagine that you have a string, and the string is fixed by 2 points, and the string is moving, okay? And you are walking away from the string, okay? And you are walking away from the string in two different ways. For example, in some function f and some function f2. So basically you have f1 and f2. So you analyze the physics of studying the moving string fixed in their ends, but you are walking away from the string in two different forms. So the physics that you are going to study in this example will be, okay, this example is limited, but I hope that you understand the idea, will be completely different. So the physics, when you are moving at some velocity from the string and you analyze, I don't know, some properties, will be different if you are moving away from the string with the second profile f2. So if you are moving fast, if you are moving slow, the physics that you are going to experiment from the vibrating string will be different. Here we are going to do in some sense the same. So I'm going to say it in Spanish. El ejemplo es restrictivo, no del todo accurate, pero creo que se entiende, de que básicamente si nos movemos de la cuerda con dos perfiles diferentes, nos vamos alejando de la cuerda de dos maneras diferentes, la física que vamos a ver va a ser completamente distinta la una de la otra. And that's the point. Sorry for that. So this is the table of contents. So we are going, first of all, we're going to review some aspects of GR on ADS3, which I review it, but I'm going to show it in more detail. We're going to see some gravitational aspects and summary. So along this talk, I will always work within the Hamiltonian formalism. That's the spoiler. So in the vacuum and with negative cosmological constants, three-dimensional general relativity can be written as the difference of two Chern-Simons action, where k is the level. And we are going to foliate or manifold with polar coordinates, t r phi, and t rho phi. I have a typo here. And also, well, the gauge fields are spanned into independent copies of the SL2R Lie algebra, and the equations of motion are, of course, that zero curvature equation. Nonetheless, this equation of motion, which corresponded to Einstein equations in the Chern-Simons formalism of gravity, is somewhat different than the one that I showed you before, ft phi is equal to 0. So we have to massage this differential equation in order to arrive to the previous one. Nonetheless, okay, we are going to proceed with the asymptotic analysis. Then I will going to massage the differential equation. So consider the 2 plus 1 splitting like this. In components, the Hamiltonian action reads like this, where notice that Fij is a constraint of the theory and He is a Lagrange multiplier. Fij is a first class constraint. He is a Lagrange multiplier. And notice that we have this B guy here. Well, this B is a boundary term that basically, if we want a differential variational principle, we must supplement the action with a surface integral that you can see here. Notice that we must specify suitable asymptotic behavior of At, a Lagrange multiplier, and A phi in order to integrate the boundary term, and then you will have a differential variational principle. Nonetheless, let me do some massages first. Well, it is possible in 2 plus 1 dimensions to gauge away the real dependence like this. So notice that with a global gauge transformations, capital A transformed like this, like B minus 1, B plus A times B. So if B captures completely the radial dependence, notice that the boundary term that you can see here transforms like this. Nonetheless, observe that this guy, by the cyclic property of the trace, cancels with this guy, and this guy is also 2. And then the variation of the boundary term will be read like this in terms of At and A phi. And these guys, At and A phi, they do not depend on the radius. So basically, the real dependence can be gauged away, as I was saying before. Now we can impose the fall-off. And this will be given like I was showing to you at the beginning of this talk regarding the crash course on integrable systems. At and A phi like this. Okay, so it is the same zero curvature formulation for integrable systems, but now we have to work with 2 copies. That's it. So when you have A phi, then you must put some superscript plus minus, and also some plus minus here, and so on, and then you will be able to arrive to integrable systems. That's my point. Nonetheless, the boundary conditions will be completely specified when you choose mu like this. Okay, this is general. It is possible to arrive to KDV or DIM. No me estoy casando without anything of KDV and DIM at the moment. So the boundary term, observe if you plug this guy here, notice that it will be given by this expression, and nonetheless by the chain rule, the boundary term will translate as your favorite Hamiltonian of your associated integrable system that you are working on. It is possible to be KDV or the dim Hamiltonians of the hierarchy. So let us construct the asymptotic dynamics. So remember that we have the capital A transforms globally like this, and now we are going to massage the equation of motion. And how it will be done? Well, notice that the zero curvature equation transforms like this. And okay, basically, then you will be able to find ft phi is equal to 0, thus arriving to this differential equation. Recall that it is the same as the one that I showed you before. And this dv, remember that operator dv separates into dw minus cdc, where dw, it is given by this expression dc like this, and c is the Brown Henneaux central charge divided by 24 pi. Why? Because I would not like to obtain undesirable 24 pi terms in the middle of the calculations. So we are ready now to define completely asymptotic behavior by imposing some mu or h. So, okay, it's the same. So for KDV, we have this hierarchy, and for DIM, we have this hierarchy. Notice the following, that for both, if you choose mu equals to 1, then you will have a phi, but these expressions will vanish, and then you will arrive to Brown-Henneaux boundary conditions. So within this formalism, Brown-Henneaux boundary conditions are encompassed here. So now I am going to study asymptotic symmetries. And as I was saying at the beginning of the talk, they correspond to the set of gauge transformations that preserve the form of the fall-off plus boundary conditions. So for the angular component, a direct variation of A phi yields this expression that you can see here. while on the other hand, applying this expression that you can see here, you will obtain this. So basically, you have to equate these two expressions, and then you will be able to find the infinitesimal asymptotic transformation of the dynamical field mathcal L, which will be given by this expression. And I will skip the details. So for the temporal component, a similar procedure can be performed, and we will be able to obtain this expression. This differential equation is very hard to solve because one must solve eta in terms of mu. Nonetheless, you have some variations of mu, and mu can be very complicated. Nonetheless, one could say, okay, so at this moment you must choose the form of mu, but no, we will not choose the form of mu. We will going to do it in general until this point. After this point, we will have to choose some hierarchy like KdV or dim. I am going to do it for KdV as a warm-up, and then I am going to do it for dim. So this differential equation like this, trust me that it may be rewritten like this. So how can we solve this equation? So we must solve this differential equation like this. Why? Because we must know the form of the permissible form of the function eta such that preserves these infinitesimal transformations, and therefore it preserves the form of the Laplace boundary conditions. So solving the asymptotic dynamics of eta, I am going to start with KdV in contrast with dim. So for KdV, we have H0. So this part will be very technical, but I'm going to skip the detail at this point, but let me do it heuristically. So notice that you have Hn here. So then you must replace your favorite H associated to your favorite hierarchy. At the moment, it is known that it is possible to arrive to KdV, and soon to be published, it will be possible to find dim. Okay, so if you replace H0, then you will have to perform the functional derivative of H0, dv of eta, and then you must solve the differential equation that you will obtain at the end of the day. That's the point, okay? So if you plug H0, then you will obtain this differential equation, and this differential equation, how can we solve this differential equation? Well, it is possible to solve it readily, but nonetheless, observe the following, is that if you plug mu zero, the mu of KdV, remember that mu zero was 1, then you will obtain 0 equals to 0, so it is trivially solved. So now if you replace mu1 of KdV, then you will obtain the chiral boson equation. So now I have a question for you. So this differential equation is the equation of motion? Yes, it's the equation of motion associated to the hierarchy that you obtain from the Chern-Simons perspective. So it is trivially solved. You obtain the equation of motion, you are done. So if you replace mu2, then you will obtain again the equation of motion, but with a complicated operator. It's solved. And so on. So you can perform the same procedure with H1, and you will obtain this differential equation. This differential equation also, it is very difficult to solve it, but it's the same story. If you plug eta mu0, you will obtain this, and if you plug eta equals to mu1, the consistency equation for the gauge parameter eta at the boundary will transform at the KdV equation, and the KdV equation is, okay, the equation of motion, so it is solved, and so on. These guys are important, mu0, mu1, and mu2. Remember that they are the functional derivatives of h of KdV. I'm working with KdV at the moment, and they are known as Gelfand-Dickey polynomials. It's just a name, but it is an important name. It is an important name. So in general, eta is solved by a superposition, of course, for the jth Gelfand-Dickey polynomial. Remember that the functional derivative of h with respect to L was mu. This guy here. So basically, it is a sum of Gelfand-Dickey polynomials. That's it. So what happened in this case? Well, in this case, it is the same. It's the same story. So if you plug H0, then you will obtain the same expression that we had for KdV. So now for H1, if you plug the first Hamiltonian of dim, then you will obtain this differential equation. And this differential equation is very hard to solve. Mathematica cannot solve it. So if you plug the dim Gelfand-Dickey polynomials, Then you will obtain dim Gelfandiki polynomials are basically the functional derivatives of dim's Hamiltonians with respect to L. That's it. So if you do this procedure, then you will obtain always the equation of motion. 0 equals to 0, it is trivially solved. Chiral boson equation is the equation of motion. 0 equals to 0 is solved. This is dim equation, and here is a horrible differential operator acting on dim equation. So for dim's hierarchy, this equation in red is solved in an analog way than the KdV hierarchy as a superposition of dim's Gelfandiki polynomials. A general proof can be given, which is, in my opinion, very beautiful. Nonetheless, it is beyond the scope of this talk. So what is the implication of eta, that eta is a superposition of Gelfandiki polynomials? Well, from the what I like from the Hamiltonian perspective, as I was saying before, is that from the Hamiltonian perspective, one can control the asymptotic degrees of freedom. And in this sense, to integrate the charges from the Rey-Teitelbaum approach, one has that the generator of charges, like the mass, the angular moment, and so on, it is given by this expression that you may read here, where lambda is given by this guy, but lambda here depends on will depend on eta. It is smeared on eta. So you will obtain this guy that you can see here. Nonetheless, as we had to fight to find that eta is the functional derivative of h with respect to L. So if you replace it, then you will have this expression here, and this expression here by the chain rule is nothing that your favorite H Hamiltonian of dim's hierarchy. So this result is very important. Why? Because this result is saying to us that the integrable system was geometrized. As Matthias was asking, I am showing you right now. I am showing you here the answer is that the gravitational charge now translates as the integrable system charge. And this gravitational charge is the one that generates gauge transformations, improper gauge transformations, the one that gives you the infinitesimal symmetry from Noether's theorem, such that you will be able to find the chart that you can see here. So this is the result. The integrable system was geometrized, and the Noetherian gravitational charge is mapped to the J Hamiltonian of dim's hierarchy. That's the point. Matthias, it was clear or not?
Well, I mean, it's clear that this is related because you proved before that H is a representation of the Virasoro algebra when you did
Yes.
yeah.
But just for KdV, not for dim, because here I was working with dim. KdV was a warm.
Okay, well, you proved it for KdV. I
Yes,
guess
and
it happened
also
for
dim.
KdV too.
Yes.
So you proved it for KdV, but
And also for dim, yes.
Yeah. What you are proving there is proving the H is a charge associated to H generator of the
It's a charge
algebra.
associated to the integrable system.
Yeah, but it's also a charge associated to the generator, no? Right? Or something like that.
Exactly. Yes,
Yeah.
exactly.
But
So
you
basically,
don't
I'm
know
saying to you that you can apply Noether's theorem on the integrable system.
Yes, but you don't know the two-dimensional safety that is dual to this.
That's a very nice answer. It is possible to obtain. So let me translate your question. You are saying that how can you read this to the CFT? Well, first of all, here I am doing holography far away from CFT, and secondly, it is possible to find a field theory at the boundary by proceeding with the Hamiltonian reduction of the Chern-Simons. Then you will obtain the Wess-Zumino-Witten, and then with the Wess-Zumino-Witten, it will be possible, for example, in the Brown-Henneaux case, you will be able to find Liouville or chiral boson, your Liouville or chiral boson theory. But here, you will be able to find an action principle for integrable systems. And action principles for integrable systems are not known.
Okay, but it will be very complicated, right? A very weird kinetic term.
Not so much.
Like
No, not so much. No,
Okay.
no, not so much. But there will be subtleties in the sense that you will obtain, for example, if you do the Hamiltonian reduction for the KdV, you will obtain an action principle for what is known as potential modified KdV,
Okay.
which is somewhat related to KdV. For DIM, we are working on that, but we expect to obtain potential modified DIM also.
Okay.
But these are in the works of, for example, in the article of Miguel and Ricardo Troncoso, Miguel Pino, Ricardo Troncoso, they do the Hamiltonian reduction, or you can also see the seminal article of Kusaert, Henneaux, and Van Driel from 95 or 98, where they obtain Liouville at the boundary.
Okay. And also, you mentioned at some point solitons. Where are
Yes.
the solitons in this? The solitons are the charges.
Yeah,
Okay.
solitons, that's a very hard question because we don't know yet. And let me answer that question when I turn to the metric point of view.
Okay. Okay.
Then I'm going to show you how solitons will play a prominent role here.
Yeah, here you are in like Chern-Simon's point of view or something like that.
Exactly.
Okay.
But then I am going to work in the metric formalism. And in the metric formalism, I'm going to show you a metric where you can plug the metric will depend on these calligraphic L's. And these calligraphic L's,
Okay.
they satisfy the dim equation. So then you can ask me, okay, so if you solve dim equation or KdV, you will be able to replace L by this soliton, the soliton that you find by solving the differential equation.
Okay.
So but the metric will depend on L, and if the metric depends on L, and if you plug a soliton, the metric will be very complicated.
So the solitons are related to the to T charges instead of the usual
Yes.
topological
Yes.
charges. You have this.
Yes.
Okay.
Yes.
Okay. Thank you.
I would like to enter my tablet here in order to do some equations to be more concrete with your question. Let me enter my tablet here.
Sure.
I already put your tablet as co-host.
I like that the
Thanks.
tablet is called tablet.
Yes,
It's
yes.
not-
Okay, so if you, for example, so the metric, when you construct the metric will depend on L plus and L minus. And remember that L plus minus solves dim equation. This is dim equation. So you can say to me, okay, Kristiansen, but solve this differential equation, find a soliton, and then with your soliton, with the soliton that you have, replace it in the metric here. But the problem with that, and it is a matter of research because there's no solitonic metric associated to an integrable system at the moment. One of the problems, for example, for KdV, it is a hyperbolic secant. I don't remember if it's cube, and it's something like this. This is the most trivial one. And this soliton has a problem, is that it is not periodic. And here I will work with coordinates t rho phi. So this soliton breaks periodicity. So you can say to me, okay, Kristiansen, work with a periodic soliton. Okay, there is a periodic soliton associated to KdV, but this is a noidal wave that depends on some parameter. I don't remember how it is. This is an elliptic function, and the elliptic function is very hard to work. I thought that it is very trivial to construct it from the KdV equation. From the KdV equation to obtain this solution is very easy. Nonetheless, to have a metric with this noidal wave that you can see here, it will be very involved to find, for example, beta, Hawking's temperature, and perform the thermodynamic analysis. But we are working on that, and we have results. But at the moment, there is no soliton. There's no solitonic solution in the metric from the metric point of view. That's my point.
Okay. Okay.
So to end the asymptotic symmetry, one can compute the asymptotic symmetry algebra with all the discussion that we had before. And okay, it is possible to compute the asymptotic symmetry algebra by using this formula. So I will skip the details, but notice the following is that if you compute the asymptotic symmetry algebra, basically you will obtain a Poisson bracket associated to the operator WB, and a second Poisson bracket associated to C. And because of the involutive nature of these conserved quantities associated to the integrable system, then the asymptotic symmetry algebra will be zero. That's my point. And this is a somewhat miracle. Why? Because, for example, forget this, and imagine that you have this. And this, observe that, imagine that you're working with KdV. This expression that you can see here is nothing but the Poisson bracket associated to KdV. But a miracle happened. The miracle that happens is that the differential operator associated to KdV, dV, separates into two other d-Hamiltonian operators, dW and dC. And these dW and dC, they form also a Poisson structure, like you can see here. So this is a miracle, and it is very non-trivial that this happened, in the sense that imagine that you are working with KdV, and I can tell it to you, okay, please give me two different b-Hamiltonian operators different than these ones. It is a very hard question, or to find two different b-Hamiltonian operators that creates well-defined Poisson brackets. It is very hard. So this is a miracle. That's what I would like to emphasize. So the take-home message: one, because the generator of asymptotic symmetries correspond to the one of Dim's hierarchy Hi, basically we can apply Noether's theorem to the integrable model. We were able to obtain the asymptotic symmetry algebra through the Poisson brackets of the integrable model. The duality says that, okay, the asymptotic symmetry algebra of gravitational charges maps as the Poisson brackets of the integrable model. Why? Because we geometrize the integrable system. We transform the conserved functionals of the integrable systems into an Noetherian one. So this result is expected. Secondly, one of the compatible b-Hamiltonian operators of the KdV hierarchy dV splits into different compatible b-Hamiltonian operators of other integrable model dW and dC, which is non-trivial. In sum, we provided a novel set of suitable boundary conditions, in the sense that they are Fallot plus boundary condition itself. For IDS3GR, they share the same Fallot than the KdV ones. So notice the following: the Fallot is telling to you that the mass of KdV and the mass of Dim are the same. The mass and the angular momenta are the same. Nonetheless, devil is in the details, in the sense that the boundary conditions produce several differences. So consider, for example, L equals to a constant, the zero mode, and N equals to 1. So you have N equals to 1. I'm going to show you here. You don't need to remember anything. Is that if you plug N equals to 1, then the mass with KdV boundary conditions is linear on L, while with N equals to 1 for Dim, the mass is a square root of L. So the physics is completely different. And also the energy is, of course, because the mass is basically the energy. The energy of KdV is proportional to L, and the energy of Dim is proportional to the square root of L. So our thought, in sum, we provided a novel set of suitable boundary conditions for ADS3GR. I thought that they share the same Fallot than KdV. You can see here that they are the same, but if you plug the mu of Dim in contrast with the mu of KdV, then the mass, it will be linear on L, in contrast with the mass is proportional to a square root of L. And the square root is different from the linear, in the sense that this guy admits negative L's and vanishing L. Nonetheless, this guy does not admit a negative L because the mass will be complex. And also you can say, okay, L will be equals to 0. It's okay. Yes, but it will have some subtleties. I'm going to show you at the moment. So now we can construct the metric, and we initiate the analysis of the geometry by constructing the metric in accordance with the following relation, with the following gauge parameter. Okay, it is possible to construct this horrible metric, but this metric will be further simplified with the following. It will be tractable with the following configuration. So we are going to work with the zero mode. So Matthias, at this point, if you want, you can work with the soliton or the noidal wave or your favorite solution that you can find from dim equations for dim equation, for example. If you can find a non-trivial solution to dim, then it is possible to replace it here, and then you will have a metric whose Einstein equations solves the integrable equation, like the soliton, for example. I don't know if it's clear at this point.
Yeah.
So
It will be like a perturbation, right? Over ADS3 or something
sorry?
like that. No? Like a Pfefferman-Graham, it will be the next order term. This thing goes to ADS3 at the boundary, I guess, right?
Yes.
So this is like a perturbation of ADS3 in the bulk. You will get
This configuration that I am working here?
Yeah. This is in the bulk, right?
Yeah, this is in the bulk. From the asymptotic dynamics, I am constructing the bulk. Yes, but it will be not a perturbation. It will be some type of Bañados geometries.
Okay.
A generalization of Bañados metric.
Okay.
But my point is that remember that this L plus minus solve dim equation or KdV, the one your favorite integrable system, right? And your favorite integrable system can be solved, and you can find the solution L equals to a constant, the zero mode, or you can find a soliton. Then you must replace it here, and then you are done. You can construct a metric associated with that dynamic. That's my point.
Okay.
So remember that mu was the functional derivative of h with respect to L. So if we consider the zero mode L, it will imply that mu is a constant. Therefore, within this constant, the metric further reduces. So now if we open the following redefinition, rewrite the above in Schwarzschild-like coordinates, in ADM coordinates like this. So you have the following lapse, which is deformed by these Lagrange multipliers mu. And you have this function f, the metric function, and this shift function that you can see here. I would like to emphasize that for mu equals to 1, you obtain Bañados metric. So we emphasize the fact that L plus minus is a solution of the stationary dim hierarchy. Remember that like this. So here now comes the point is that the configuration L equals to 0 is not permissible. Why? Because dim equation has a square root in the denominator. So the configuration L equals to 0 will be forbidden at this point. And this will have implications from black hole configurations. So the last section is gravitational aspects. And okay, I'm going to work within the metric formalism at this point. So we have the following metric, and the horizon radius is given by this expression that you can see here. So what about extremality? Well, extremality will be given by when this guy vanishes, and this guy vanishes when L plus minus is equals to 0. Nonetheless, because the mathcal L fulfills dim equation, then extremal black holes will be not included within this spacetime. Regarding the mass and angular momenta of dim's black hole, okay, I calculated before, but it will be given by this expression. And the black hole solution spectra is divided in the following phase space portrait, like you can see here. So extremal configurations, which are not permissible within the solution, in the zero mode solution, are not permissible, and this stands for the dashed lines. So basically, our black hole lives inside here, in this area. Regarding Hawking's temperature, after, for example, a near horizon analysis of the Euclidean metric, or from the holonomy point of view, or also with the zero law, it is possible to find the following behavior. Beta is a constant quantity. When beta is a constant quantity, this behavior is known as Hagedorn behavior. So what is the possible consequence of this feature? Well, I would like to emphasize that for KDV, you don't have this behavior, Hagedorn behavior. Hagedorn behavior is something that emerged also in QCD and also in string theory. Nonetheless, here, at least at the best of my knowledge, I don't know if it was shown before. Maybe I'm wrong. So what are the possible consequences of Hagedorn behavior? In order to analyze the consequence of this feature, consider the first law of black hole thermodynamics for the Brown Henneaux boundary conditions, like this, in the grand canonical ensemble. Here, mu J is the chemical potential associated to the angular momenta, and the angular momenta is given in terms of these zero modes, L plus and L minus. So, okay, it is possible, I will skip the details, but if you rewrite ABH in terms of L plus minus, then it is possible to go from the grand canonical ensemble, in the Brown Henneaux ensemble, to the Brown Henneaux chiral antichiral ensemble. Like, let me show you, like this. So basically, this is the chiral antichiral ensemble, and it is possible to find, after some algebraic steps, which are very direct, that beta of Brown Henneaux plus minus, it will be given by this expression that you can see here. Okay, so now we will go to Dean's chiral antichiral ensemble. Okay, and the beta of the inverse of Hawking's temperature of every sector will be given by this expression that you can see here. So now I will move with this to the chiral antichiral ensemble. So recalling that the energy, this is important, that the energy of Brown Henneaux is linear on L, and the energy on DIM is proportional to a square root of L plus minus, then it is possible to rewrite the energy of Brown Henneaux proportional to the square root of the energy of DIM. Why this is important? Because here you will have a variation of the energy of Brown Henneaux. So if you replace it here by applying it by taking direct derivatives, then you will be able to find this expression that you can see here. And now, if you recognize like this beta plus dim and beta minus dim like this, okay, you will be able to find this guy here, which is in agreement with this expression that you can see here. So, okay, we had Brown Henneaux ensemble, Brown Henneaux chiral antichiral ensemble, Dim's chiral antichiral ensemble, and now we move to Dim's grand canonical ensemble in order to get the point of what are the consequences of Hagedorn behavior from the gravitational point of view. So, okay, this step, you can skip it, but if you go to Dim's grand canonical ensemble, you will obtain this expression that you can see here. And notice the following, that, okay, this is the chemical potential associated to the angular momenta of DIM, of the DIM system. And notice the following, this is very important, that remember that beta DIM of every sector was constant, right? So basically beta plus and beta minus are the same. And that's the reason that Hagedorn behavior will imply that the chemical potential of the angular momenta will vanish for our dim black hole. So what does it mean, this result, physically speaking? Well, it means that this black hole, dim black hole, will lie naturally in the canonical ensemble, not in the grand canonical one, because mu j vanishes. It lies naturally in the canonical ensemble. This is a consequence of Hagedorn behavior. What are the other consequences of Hagedorn behavior? Well, before exploring more consequences, it is reassuring to compute the entropy by means of the Hamiltonian approach. So, okay, the boundary term in the Rayet-Teitelbaum approach from the gravitational perspective is like this, and you will be able to find this guy where the entropy S0 will be given by this expression, which is nothing but the Bekenstein-Hawking area law. Okay, that's a cross check. as expected. Okay, so we're working with GR. Bekenstein-Hawking area law is holding at this point. So what are the consequences of Hagedorn behavior? The second consequences are log corrections. So logarithmic corrections to the Bekenstein-Hawking entropy S0 acquire the following general form, like this, where Q is a numerical factor that depends on the dimension, thermodynamic ensemble, and matter content. So notice that the objective here is to find Q. Nonetheless, observe the following, is that if we understand this expression as a saddle point approximation of the density of the state rho plus minus from the statistical mechanics point of view, like in the Landau-Lifshitz book, quantum fluctuations to the entropy are determined by this expression that you may read here. Observe that it depends on the heat capacity. However, beta dim is a constant quantity. So this means that the inverse of the heat capacity vanishes. So this means that it seems that there is no room for thermal fluctuations in this black hole. It seems that this black hole does not admit log corrections, or in other words, it is a pure classic result. Nonetheless, it is possible to solve this problem. We can find the quantum fluctuations to the entropy according to the following procedure. The answer is to change the ensemble. So following the procedure of Pathak, Porfiriadis, Strominger, and Varela, you can see the article from details. It is possible to go from Brown-Henneaux ensemble to the DIMS one. How? By according to the following procedure, it is basically a Jacobian factor in the density of states of DIM. So what does it mean, this method? This method is very important because, okay, you know the density of states of Brown-Henneaux. It is very well known. For DIM, you don't know it. Nonetheless, you know how the energy of Brown-Henneaux is related to the energy of DIM. Remember that the energy of Brown-Henneaux was proportional to the square root of the energy of DIM. So basically, you must compute this Jacobian, which is very trivial to compute, and you are done. Therefore, because the entropy is the logarithm of the density of states of DIM, then notice the following. We can compute the logarithm of this quantity that you can see here. So the logarithm of this quantity will be given by, okay, because the logarithm in the multiplication sums, we will have the logarithm of rho of Brown-Henneaux, like this, plus this log correction that you may read here. And this quantity is known. So for the Brown-Henneaux case, the logarithm correction reads like this. It is a very well-known result. S0, remember that S0 is the Bekenstein-Hawking area law, like this. Therefore, for each copy, then you will have this guy. The entropy of DIM will be corrected by the associated logarithmic correction of the Brown-Henneaux case, plus the contribution from the Jacobian. And that's it. So as I was saying, because the energy of Brown-Henneaux is proportional to the square root of DIM, okay, subtracting is just a subtraction. You can find this expression. Therefore, you find that the Q of DIM is equals to 1. And we were able to compute log corrections to DIM's black hole. So to end this talk, summary and future prospects. So novel asymptotic fall-off plus boundary conditions were imposed. We showed that although they share the same fall-off than the KDB ones, its asymptotic structure is completely different and yield a complete different black hole thermodynamics. And its consequences were analyzed from the Chern-Simons and the metric perspectives. Hagedorn behavior is present and has strong physical implications. Also, black hole configurations are allowed, but not its extremal version. I would like to emphasize that for KDB, there is an extremal black hole, but here not. Also, the Bekenstein-Hawking area law holds and log corrections were calculated. So future prospects, solution like Matthias was asking, solution beyond the zero mode, like a soliton. We have results, we are working on that. Also to obtain the Hamiltonian reduction, like the boundary field theory that captures the asymptotic degrees of freedom, and also to explore the flat counterpart by performing like an Wigner contraction at the level of the boundary conditions by taking L, the EDS3 radius to infinity, and redefining the dynamical functions L, the mathcal L. So this was my talk. Thank you very much.
Thank you, Kristiansen, for your very complete talk. Okay, perfecto. Is somebody, let me stop the recording and then we can start with the questions.